So make sure you pay attention to what's on the website. It's section 6.2. If I'm really nice, I'll write this at the end of the lesson. 6.2, numbers 57 through 61. Okay, so we can read through this really quickly here. It says an interesting application for the use of ellipses is if an elliptical tub in the non-surgical removal of kidney stones. Luckily, in my life, I've never had kidney stones. I hear that they're really painful. But in this procedure, the reflective property of the ellipse is used if a beam is projected from one focus onto the ellipse. It reflects off of the ellipse and goes to the other focus. So what we do is you kind of place the patient at one spot where a focus would be and the beam at the other. And if you shoot this laser beam off the side of this elliptical tub, it would reflect off of that and hit the other focus, which is where you're going to place your patient with their kidney stones. So this fancy name for the machine, by the way, is called a lithotripter. Okay. So then from there, it says if the lithotripter is based on this ellipse equation, x squared over 36 plus y squared over 27 equals 1, determine how many units the kidney stone and the wave source must be placed from the center of the ellipse. So since the wave source and the patient's kidney stone have to be at the foci of the ellipse, we have to find the value c. So where are the foci located? To do that, you're going to find little c. Now, remember, based on this equation, we know the values of a squared and b squared. So we know that a squared is 36. I'm going to use the equation a squared equals b squared plus c squared. So 36 would equal 27 plus c squared. If you subtract 27 to the other side, 9 equals c squared, and therefore we get, if I take the square root of both sides, that c equals 3. Now, I'm going to be completely honest. This might be just one of those teacher-contrived problems. So what I mean by that is I pick some kind of nice numbers here such that in the end you get a really nice value of c. So how would I answer this? Well, the patient and the wave source must be placed 3 units from the center. I'm just going to use the generic term units because I don't really know what that means. Is it 3 feet? Is it 3 inches? I actually don't know the answer to that. All I know is I'm going to tell the doctor, place them 3 away, whatever that might mean. Okay, so here's where math and real life collide, but my lack of knowledge of other things that are not ellipse related is failing me here. So look it up. Let me know what you come up with. All right, true story though. This is a real thing. Here's a picture of it. Okay, moving on to number 2. Number 2, this is, I think, a little bit more of a classic example involving the application of ellipses. You know, when we talk about planetary motion happens in an elliptical orbit. So it says the Earth revolves around the sun in an elliptical orbit where the sun is at one of the foci. And this was discovered by Kepler in the year 1610. Pretty smart thinking back in the early 1600s. The major axis is approximately this long in kilometers. And it is known that the ratio of C to A is equal to 1 over 60. I'm going to talk about that a little bit more in a moment, but it says, what are the greatest and least distances that the Earth can be from the sun? So let's think about this for a moment here. It says the sun is located at one of the foci. So if here is the path that the Earth is traveling in, let's kind of put the sun over here. If this is one of the foci of the ellipse, the closest I can get to the sun is going to be at this location right here. And the furthest away I can get from the sun is going to be at this location over here. So I want to somehow define, how can I determine those two values? Okay, if this is a focus, these are the vertices, right? V and V prime. And this is the center of the ellipse. So how would I define the distance from the sun to this furthest point away? Well, we know the distance from focus to center is C. And we know the distance from center to vertex is A. So that's going to be simply the sum of A plus C. And then on the other hand, if I wanted to find this little distance right here that connects this vertex to this focus, that's the closest I can be to the sun, that would be the total distance to the vertex A minus C. Okay, so this one over here can be calculated by finding A minus C. So that's what we have to do. We have to figure out what is A and what is C. Let's use some of the info. The major axis is approximately this long. So if that's the length of the major axis, remember, you can divide that by 2, and that's going to give you the value of A. So if you divide that by 2, the value of A is going to be 149,597,871 kilometers. Okay, now that I have the value of A, I also need to know the value of C. We're given, in this case, the ratio of C over A is 1 to 60. So if I set up the proportion 1 is to 60 as, okay, that's the ratio of C over A, as C is to this value of A, that very large value there. You can set up a quick proportion there using that ratio C over A. And if you cross multiply, you're going to find that C is equal to 2,493,000. Very large numbers here, right? 297.85 kilometers. Okay, so now that we have established here the values of A and C, we can get our greatest and least distances. Okay, so the greatest distance, which we determined was A plus C, is going to be the sum of those two things, which is 152,091,168.9 kilometers. And then the least distance between the Earth and the Sun would be the quantity A minus C, which in this case is, if you subtract those, 147,104,573.2 kilometers. Okay. Sorry, I kind of had to squeeze all that in there. It is a little bit tough when the values are as large as they are in this context. But I said I would come back to this ratio C over A. This might sound familiar from maybe those earth science days. This is known as the eccentricity of the ellipse. And the eccentricity is kind of a nice value to have a context of, because if you know the eccentricity, it tells you either how circular the ellipse looks or how flat it looks, okay? So I'll tell you, the closer the eccentricity is to a quantity like 0, that means that the ratio C over A, that the distance center to focus is not really a lot. It's really much more center to vertex there. That's going to look more like a circle. In fact, if the eccentricity is 0, it is a circle, because the distance from the center to focus, the focus would be right on top of the center. If you get all the way to an eccentricity of 1, you don't have an ellipse either. You actually have a flat line segment, okay, that connects your points across through the major axis there. So the closer you get that eccentricity 1, the more flattened pancake looking it looks. But the closer the eccentricity is to 0, it starts to look more like a circle. All right, question here, how far is the Sun from the other focus? So we're kind of curious here about what's the distance from F to F prime, and that's just going to be a length of 2c. So since we've already calculated c up here, doubling that gets you 4,986,595.7. What's at the other focus? I have no idea. Again, it's sort of like I have no idea what 3 units meant up here, but it's kind of cool that we can talk about it. I mean, I can get a little bit more context about understanding the closest and furthest that we are from the Sun, but even those huge values, it's really hard to, understand the magnitude of just how how great of a distance that actually is. Okay. The one that I said we would skip today is actually number 3. So don't worry about number 3. We'll skip this about, it sounds nice, about a tour boat around an island, but we're going to go right to the last example here, which is about a tunnel. And I believe there's a question like this on the homework as well. It says a train track runs through a tunnel through a mountain in the form of half of an ellipse. So here's that path right here, that half of an ellipse. The tunnel is 20 feet high at the center and 16 feet wide. Assuming a train is 10 feet wide, what is the height of the tallest train that can pass under the overpass? We're going under the overpass. All right. I'm going to kind of recreate this off to the side. Okay, so here's my tunnel picture. And I'm going to say that's the center of this little half of an ellipse. And going back to the information, it's 20 feet high at the center. So this is 20 feet right here. and it says it's 16 feet wide. So I guess if it's 16 feet from here to here, that these distances would be 8 units each to get a total of 16 feet. All right, so I think we're probably okay with that. And what I want to know is if a train is 10 feet wide, remember 10 feet wide in this context would be if I go 5 feet this way and then another 5 feet this way, that would be my total of 10 feet wide. I'm kind of curious, like what's the highest, what's the tallest that train could be? Okay, such that we're not going to have a big train accident in this case. We want to avoid that at all costs. Here's how we're going to approach this. We're going to have to come up with what is the equation of this elliptical path. And then what we're going to ask ourselves is, all right, well, if this distance is 5 feet away from the center, what height does that correspond with? I want you to think of almost like a piece of graph paper laying over the top of this right now. So what I'm asking you is when I go 5 feet to the right of the center, and just to make our lives a little bit easier, I'm going to call the center of the ellipse 0, 0. You can choose whatever you want and you'll still get a correct answer, but why not call it 0, 0, just to make our jobs easier? So this point up here becomes the point 5, comma, y. That's what I'm looking for. What is that height when I go 5 feet away from the center? I hope you understand why I'm using 5, by the way, right? Because if the total width is 10, based on where that axis is drawn, we're going to cut that in half. All right, so what's the equation of that ellipse? We know that the center is 0, 0. We need to start finding the values of A and B. Okay, so A is center to vertex. B would be center to the end of the minor axis here. These little axes here that are going from the center, one has a length of 20, one has a length of 8. So we know that A is 20 and B is 8. And since the larger of the axes is going up and down, the major axis here should be vertical. With that being said, these are the key components that we need to write the equation. So it's going to be x squared over b squared, which is 64, plus y squared over a squared, 400, equals 1. Are there other possible ways to do this? Like, could I have put the center here and called that, or sorry, could I have put 0, 0 here? Sure, then this would have been the center at 8, 0, and I could have gotten the same results by doing it that way. All right. All right, but since we have this equation, it looks pretty nice, centered at the origin, let's go ahead and do what we're trying to accomplish here. We said if we go 5 away to the right, what's that height? So we're going to plug in 5 for x, and we're going to solve this for y. So 5 squared over 64 plus y squared over 400 equals 1. Okay, so that's really 25 over 64. So if I subtract this to the other side, 64 over 64 minus 25 over 64. Going to kind of keep this in a fraction sense. It's going to be 39 out of 64. Okay, and if we continue to solve for y, maybe we'd cross multiply next. 64y squared is equal to 15,600. Okay, divide over the 64. This equals 243.75. And then finally, square root, square root. Okay. Now, technically, when we square root, we would get a plus or minus answer here. We really only care about what's the positive y value. The negative y value would be if we looked at the entire ellipse that comes kind of like underground here. Okay, but the square root of 243.75 is, okay, approximately 15.61 feet. So in the end, I would say that as long as you have a train that's like 15 feet tall or less, we should be pretty safe. And I would say for a question like this, just pay attention to rounding if it says to the nearest foot or something like that. If I said to the nearest foot, definitely we don't want a 16-foot tall train. That's not going to fit under. But let's say that a 15-foot tall train should be able to fit in there without too much of an issue there. Okay. So that's pretty much it. These were a good variety of ellipse applications. We talked about the lithotripter, getting rid of those bad kidney stones. We're gonna, take some trips around the sun on planet Earth, and we want to get under the tunnel without having a train crash. So let me know if you have any questions about this stuff. Again, the book homework that I mentioned, I said I would be nice and I would write it for you here. So that the homework is from section 6.2. numbers 57 to 61. Okay? If you have any questions, I'll see you at the Google Meet. Otherwise, enjoy the rest of the day.